anytime our object is in motion, we need to start thinking about it in terms of what's changing, right? What's changing? That's going to be our focus for most of really first semester physics is how is this object changing? Is it getting faster? Is it getting slower? Is it moving forward, moving backwards? Is it speeding up or slowing down, right? All of these kinds of things. And so when we start talking about motion, there's going to be a couple different versions or a couple different ways we look at motion. The first and most basic kind of motion is straight line motion. That just means when something moves very simply from point A to point B in a straight line, right? That's going to be what we start with. And that could mean straight line vertically or straight line horizontally, right? It can mean either one of those things. We're going to start with horizontal motion, and then we'll move into vertical motion. Circular motion takes on a whole different kind of personality, right? Circular motion means we're moving in a circular pattern, but it does not mean that we're necessarily spinning or rotating. There's a difference in that, right? A circular motion would be just walking in a circle. Spinning and rotating has a little bit of different path. Okay, arc motion. What is an arc? Can you make that like movement with your hand? What's an arc look like? Right, it goes up and comes back down. It goes like this. That's an arc, like a half circle kind of. Right? So this motion is called really projectile motion. When we shoot something into the air, it goes up, then comes back down. Okay? And during this whole process, it's moving both horizontally and vertically. So we're going to see a mix between those two things, right? It's still moving horizontally and vertically. That's called projectile motion. And then back and forth motion would be examples like a pendulum. Do you know what a pendulum is? A pendulum swings back and forth. You see them in clocks a lot, right? It hangs like this and swings back and forth. All right, that's an example of a pendulum. All right, so we'll see all these different types of motion eventually. But what we need to focus on is how is it changing? Is it position changing? Is the speed changing? All that kind of stuff. So that's what we're going to look at. Basics. Okay, so we're going to start with straight line motion. You don't have to write this part out. I just want you to visualize. Straight line motion is the most simplistic type of motion, right? Our car starts at point A, it gets to point B. That's it, right? That's what we're going to start with is straight line motion. We're always going to relate motion to a position and a time, a place and a time. So here's where it started, here's where it ended, here's how long it took to get there, all that kind of stuff. Okay, so you don't have to write this part down. We just want you to visualize this. This right here is called a motion diagram. As simple as it is, it's going to be called a motion diagram, and we'll use quite a bit of that. Okay? The way we can start putting our motion into diagrams is called a graphing system, or we can call it a motion diagram, but we're going to use a coordinate system to help us do that. Okay, so when I say coordinate system, hopefully you are picturing a graph, right? You know what I mean when I say coordinate system? Okay, when I talk about a coordinate system, I mean a graph like this. Okay, do you recognize that? That's what I mean when I say coordinate system. When we're looking at our motion, we get to always pick where are we viewing the motion from? Where's our starting point? And wherever our motion starts from, we're going to call that our 0 point or the origin. Okay, the origin is right there on a coordinate system. And so when we're picturing motion and talking about motion, we're going to look at, okay, if we started here and we ended up here, how far did we go? Right? Those are the types of things we're going to talk about, the types of questions we're going to ask. Okay? So in our straight line motion, there's a couple of terms that we need to know the difference of. Distance and displacement. Okay? Go ahead and write down this definition. Distance is the total amount of length covered. The total amount of length that we covered. All right, when we think about distance, that seems pretty self-explanatory. Let's say we walked 4 meters this way, and then we walked 8 meters this way. We would have had a distance of how many meters? 12, right? But displacement is a whole different way we think about how far we went. Excuse me. Displacement, the definition for displacement is how far we end up from where we started. Okay, that's not the book definition of it, but that's what I think the most simplistic definition of it is. How far we ended up from where we started. So how is that different from distance? Right? In this example, how is that different from distance? Here's where I started. Here's where I ended up. So what would my displacement be? Yeah, a straight line between those two. And so in this case, I would find the hypotenuse of that triangle, right? And that would give me my displacement. So if I took, do you remember how to find hypotenuse of a triangle? Pythagorean theorem, a squared plus b squared equals c squared. So if I find the hypotenuse of that triangle, that tells me that my displacement is 8.94 meters, right? I walked a total of 12 meters in terms of distance, but my displacement is 8.94. So they mean two different things, and it's really important for us to understand the difference between those two. We, more often than not, will use displacement in our values, in our calculations, all that kind of stuff. We will use displacement much more often than we will use distance. Okay? So there's kind of an introduction to those. We're going to go into those a little bit deeper, but you do need to know the difference between those two things. Okay? So displacement, like I said, is how far you ended up from where you started. We use the value x for displacement. Okay, the variable is x. Okay? That's our variable for displacement. So if we're solving for how far did something go, x is the variable we use. Okay? If we're looking at vertical displacement, we would use the variable y. Why do you think those two are different? Or why do you think we label them x and y? So x equals horizontal displacement. Okay, and y equals vertical displacement. Those things match the axes on your coordinate system, right? The x-axis is our horizontal axis, agreed? And the y-axis is our vertical axis, yes? So that's why we label them x and y. Okay, so our displacement x is how far are we moving along the x-axis. Displacement y is how far are we moving along the y-axis, right? Pretty simple. All right. Displacement is what we call a vector quantity. Okay, a vector quantity. So a vector quantity is any measurement. Let me rewrite this a little bit because I want to make it a little bit more clear. A vector quantity is any measurement that must have both magnitude and direction. Okay, a vector quantity is any measurement that has to have both magnitude and direction. Okay, any measurement that has to have both magnitude and direction. Displacement is an example of a vector quantity. Okay? So vectors is a big category of measurements. Right? There's a lot of different types of measurements that are vectors that have to have magnitude and direction. Displacement is one of those things. Velocity will also be one of those things. Acceleration will be one of those things. Forces will be one of those things. There's lots of different types of vector quantities, but displacement is the first one we learned about. So when we say it has to have magnitude and direction, that means it has to have the size and it has to have the direction. So 10 meters is our magnitude. South is our direction. Okay, 10 meters would be our magnitude, south would be our direction. When we look at vectors, when we draw them with an arrow. Okay, we draw vectors with an arrow, and we try our best to draw them to scale. Do you know what I mean when I say drawn to scale? Okay, so let's look at what that means. When I say they have to be drawn to scale, that doesn't mean we have to get out a ruler and actually write up a scale to draw it. But what it does mean, if I have a vector that's 5 meters, and I have a vector that's 10 meters, do those look like they're drawn to scale? No, right? The 10-meter vector should be twice as long as the 5-meter vector. That's what I mean when I say drawn to scale. We should draw them to a proportional scale so that they make sense relative to one another. There will be times where I do exclusively ask you to develop a scale and draw them to a scale where I would say 1 meter equals 1 centimeter on my scale, right? We'll have to actually draw them that way, but not super often. Okay, so these are vectors. We draw them with an arrow, and we draw them in the direction of the motion. So wherever we're going, we're going to draw them in that direction. And we'll dive into that a little bit more in a second. Okay? The counterpart to vectors is a measurement called a scalar. Scalars are, I'm going to take this out, measurements that only have a magnitude. They only have a size. They don't include direction. So these are things like distance, time, and temperature. Okay, measurements that only have a magnitude. So I want to look back at our original example that I kind of just drew up there. Let's say we walk 4 meters, then 8 meters. Right? That was the example I gave you a little bit ago. 4 meters, then 8 meters. And I said that our distance traveled was 12 meters. Right? We said our distance traveled was 12 meters. And so that means the total amount of length that I covered, 4 plus 8 is 12 meters. So do you agree with that part? Why can't I have a direction on my 12 meters? Did we go one direction the whole time? Right, we went 2 different directions. So there's no way I can even have a direction with that, right? I can't have a direction with my distance because I went 2 different ways. But if I was looking at displacement, we said is the distance from where I started to where I ended. I can have a direction here, and it's going to be the angle from which I left the origin. Right? So I would say it's 8.94 meters. I'm going to make this up right now at 32 degrees south of east. Right? That would be my magnitude. This would be my direction. Right? And we're going to start learning how to calculate those things to tell exactly what direction did we leave my starting point to end up where I want to end up. Right? That's the difference. So distance just tells us how far we went. Displacement tells us exactly how to get from where we started to where we want to end up. All right, good. So vectors and scalars. Scalars are things that don't have to have a direction. All right, we're going to talk about how we add our vectors graphically. So how do we draw them correctly to get us to our final spot? Okay, we draw our vectors to scale. We already talked about that. We use what's called the tail to tip method. The tail is always at the starting point of the motion, and the tip always goes in the direction of the motion. So when we looked at that first example, here's my starting point. Why do you think I draw this little crosshairs? What do you think that's representing for me? Right? It's representing my coordinate system, my graph, right? And it's representing my, what's this 0 point called? The origin, right? It's representing that, but I don't want to take up my whole paper drawing a coordinate system. So I always just draw little crosshairs, and that's representing to me, this is the origin. This is where my motion is starting. Does that make sense? I'm going to recommend that you do that when we start adding vectors. Draw yourself the origin. Tell us, where are we starting the motion from? And then when I went to draw my vectors, I said we went 4 meters east. So I drew my vector in the direction it's going. I started the tail, right? The tail is here. The tip is here. And then from there, I went 8 meters south. So I don't go draw another vector from the origin. I draw it tail to tip. So tail to tip. Right? When we add them, we go one right after the other. Okay? That's called the tail to tip method. You are going to have to be able to do this correctly. Right? You're going to have to be able to add vectors and draw them correctly like this. So when we say tail to tip, it just means drawing one vector right after the other. You don't start over again at the origin. Okay, so tail to tip. So let's say we went 4 meters here, 4 meters here. Let's say we went 6 meters this way. Let's say we went a meter this way, a meter this way. Right, wherever we go, we can add as many vectors as we want. Right, we made this big loop around wherever we started. And then if I wanted to find out how far am I from where I started, I would just take a vector and I would start from the origin to the tip of my last vector. That purple vector right here gives me my displacement. Right? The red ones added together give me my distance, but that purple vector gives me what's called the displacement. Does that make sense, how that works? All right, tail to tip is super important. All right, once we get to that place where we draw that purple vector, that's called our resultant vector. It's the sum of all of our vectors in our diagram. That's called the resultant vector. And in my last example, it was the purple one, okay? So I'm going to draw that out here. The resultant vector always goes from the origin to the tip of the last vector. So let me draw another example here. We go here, let's say we go up, then we go there, here, wherever. Right, we do all of these crazy things. My resultant vector, I'm going to draw here in red, is the graphical sum. So all it's telling me is how far are we at the end from where we started. Okay? And so to get that, I go from the origin to the tip of the last vector. From the origin to the tip of the last vector. So you see all of these purple vectors are added tail to tip. One right on top of the other. But to get our resultant vector, we go from the origin to the tip of the last vector. So that when I find the value of this resultant vector, I can say, to get from my starting point to my end point, I need to walk this many meters in this direction. Right? I'll be able to find what's the angle there, I'll be able to find the length of that vector, and I'll be able to say, if you want to go from start to finish, here's how you do it. Right? That's the resultant vector, and that's what that tells us. Does that kind of make sense? Resultant vector always goes from the origin to the tip of the last vector. Okay. Any questions about what that looks like? All right. So let's go ahead and try a basic problem here. Let's say you don't have to draw this part out, but I'm going to draw it out right here. The runner starts at the origin. They go forward 2 meters, so 1, 2. Then they go backward 6 meters, so you go from the tip of the last vector, 1. Let me draw it in a different color so we can see it. 1, 2, 3, 4, 5, 6. Next, what do we do? Forward 4 meters, 1, 2, 3, 4. And then we go forward 5 meters. 1, 2, 3, 4, 5. So I added all my vectors, one right after the other. And so what's my resultant vector here going to look like? It goes from the origin to the tip of the last vector. Right? So my resultant vector, my displacement is 5 meters forward. Right? You can write out forward if you want. 5 meters forward. That's my resultant vector. I'm going to end up 5 meters from where I started. When we deal with exact or perfectly horizontal motion, it's really easy to find our displacement, right? But when we start dealing with things in 2 dimensions, x and y directions, then it gets a little bit more tricky. Okay, so questions about that resultant? Okay, good. Something else we should start to think about is that when we have negative values, they only indicate direction. So for our purposes here, let's say I go negative 5 meters. That would mean I would go backward 5 meters. The negative just tells us direction, positive just tells us direction. So if we wanted to label this, we could just go our resultant is plus 5 meters if we wanted to. Okay? Just something to think about. Let's try this one together. Okay, so here's my two vectors. It says I go 11 kilometers north, then 11 kilometers east. I'm going to say that each of those grid are 2 kilometers because I didn't give myself quite enough room. So I'm going to go north, then east. Here's something you should know when you add vectors, right? This is called vector addition. Basic vector addition. When I add vectors, it does not matter what order I add them in. I could go east first, then north, or I could go north first, then east. It doesn't make a difference. But I'm just going to do them in the order they say. So 11 kilometers, here's my origin. I'm going to go 2, 4, 6, 8, 10, 11. A little bit past there. And then on top of that, I'm going to go 2, 4, 6, 8, 10, 11. Right? Does that make sense how I drew that? So my resultant vector goes from where to where? From the origin, good, to the tip of the last vector. Okay, so I know the sides of this are 11 and 11. So now I want to find how far am I from where I started? What's my resultant? What's my displacement? And so to do that, I have to find what's that side of my triangle and in what direction did I leave my origin from. Okay, so go ahead and grab your calculator out if you don't have that out. We're going to get really good at working with right triangles. All right, we're going to work with right triangles almost exclusively. The good news is we don't have to work with non-right triangles, hardly ever. Right, we're going to deal with right triangles a lot. So this is a right triangle, and I need to do what to solve for the hypotenuse of that triangle. Do you remember the terms for triangles, first of all? This is the hypotenuse. Here's my angle. So what would this side be called? The adjacent and the opposite. Do you remember those terms? Kind of. Do you remember sine, cosine, tangent? SOHCAHTOA? Are those things coming back a little bit? Okay. You don't have to know that part just yet, but I want us to think about that for as we move forward, okay? So to find the hypotenuse, I'm going to use Pythagorean theorem. A squared plus b squared equals c squared. Right? This would be A, this would be B, this would be C for my triangle. Agreed? Do you remember how to do Pythagorean theorem? Okay, so let's go ahead and solve that. We know that that hypotenuse and that value should be greater than what? It's got to be greater than 11, because if both my sides are 11, tell me what you get? Perfect. 15 point, we'll just round it up here. 15.6 kilometers. So that's how far I am from where I started. Right? By the way that the crow flies or whatever, if I was going to look at an aerial view, from where I started to where I ended up is 15.6 kilometers. We agree with that part? So that's my magnitude. But we know that displacement is a vector, so it also has to have direction. Has to have direction as well. And so we need to find what's this angle here. What's the angle from which we leave our origin to find that last place? So let's see here. If I'm looking at this right triangle, I know all of my side values, right? I know the opposite side, the adjacent side, and the hypotenuse side. But here's what I'll tell you. When I'm solving for the angle, I like to use the values we were given to start, which means I want to use the opposite side and the adjacent side. Do you know why I want to use those two known values? Because if I calculated my hypotenuse wrong, then I'm going to calculate my angle wrong too if I use that. Does that make sense? So I'm going to find the angle here using tangent, because tangent is equal to opposite over adjacent. Do you remember those parts? No. Okay, why don't you write them down if you don't remember them. Sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. Okay, and really you should think about this. It's really sine of some angle theta, cosine of some angle theta, tangent of some angle theta. Okay, this is sine of some angle equals opposite over hypotenuse. Cosine of some angle equals okay? We might need to spend a little bit more time with right triangles. Okay, that's fine. So I'm going to get you through it today, and then we'll dive into a little bit more. So, okay. I know that I want to use tangent of some angle equals opposite over adjacent. I don't know my angle, so that stays theta. So tangent of theta equals opposite side, which is there, 11, over adjacent side, which is 11. So in my calculator, when I'm solving for the angle, I have to hit second tangent. So in your calculator, it will look like this. Tangent -1 equals 11 over 11. So go ahead and do that. Second tangent, 11 divided by 11. And we really should have known it was coming out to 45 degrees, right? Because both of our sides of our triangle were the same. Did yours not come out to 45 degrees? Okay, check your mode to make sure it's in degrees, not radians. So up here, right by the second button is a mode. You want to make sure that degrees is dark. The third line down. And you go over and select it until it's dark. Okay. Did yours come out content at 45? Okay, good. Robert, yours come out at 45 or not quite? So if you go to the mode and then scroll down the third line, you want degrees to be dark. The only time you would use radians would be like in calculus. So otherwise your calculator needs to stay in degrees because we need it in degrees in this class. Okay, so now try it again. Second tangent, 45 over 45, no, 11 over 11. And we get 45 degrees, right? Okay, so we're almost done with our answer here. Okay, our final answer for our displacement has to be magnitude and direction. So we have our displacement 15.6 kilometers at 45 degrees. What? 45 degrees in what direction? Right? Here's our cardinal directions. North, east, south, west. So which direction did we leave? We leave 45 degrees, but where? Which direction? Here's the part of our answer that some people stumble on a little bit. We are going to leave right here, 45 degrees east of north. Right? We can't just say northeast because for angles that are not 45 degrees, that means two different things. Okay, so let me show you, how did I figure out it was east of north? Right? Let's get rid of some of this stuff here. Okay, so my angle looked like this, and we found this angle right here. So how did we know it was east of north? Well, the first thing I want to look at is what axis line is my angle touching? Okay, what axis line is my angle touching? The north, the east, the south, or the west? Which one is my angle touching? It's touching the north axis. So then I decide, does my triangle swing east of north or west of north? It swings east. So that's how I found east of north. Right, just like that. Pretty simple, huh? So I find out what angle is it touching, what axis is it touching. Then I decide, does my triangle swing east of north or west of north? And that's how you can determine which direction your angle has to have. Okay, does that make sense? That's super important. All right, last thing we're going to look at here, and this is kind of a big one, is velocity. Okay? Velocity is our change in displacement, not direction, change in displacement divided by change in time. Change in displacement divided by change in time. It is a vector quantity, which means it has to have magnitude and direction. Okay, it has to have a vector. It is a vector quantity, which means it needs to have magnitude and direction. The direction part of it is the most important and the one that we forget a lot. Right? The magnitude is just the number, so that seems obvious, right? But we have to include direction. Remember I said how direction can be a positive, negative, or a cardinal direction, north, south, east, west, right? So what would a negative velocity mean? You're going backwards, exactly. Negative velocity means you're going backwards, okay, or in the negative direction. So you could be going downward, right, backward or downward, whatever your coordinate system says. The units for velocity are meters per second, or it could be kilometers per hour, or miles per hour, or whatever it might be. It's any sort of length divided by time. Any sort of length divided by time is a velocity unit. Most often, we use meters per second. Okay, most often we use meters per second. The thing we have to look at is if our velocity is measured in meters per second, and our time is measured in hours, we would have to convert this to match that unit. Does that make sense? These units within this triangle equation need to match. So if my velocity is meters per second and my unit for time was given in hours, I need to convert that to seconds. Right? We have to make sure those things match. All right, we're going to get through here and let's try a couple before we run out of time. You need to drive 40 kilometers east in 32 minutes. So what will your velocity be in meters per second? So velocity is what I'm looking for. We're going to start making a list of our variables in the margin, right? I said kind of on day one, that's super important for us to know what we're looking for, all that kind of stuff. So velocity is what I'm solving for. My displacement, or x value, is 40 kilometers. And my time is 32 minutes. I'll tell you now, it's going to be easier for us to convert these values before we solve for velocity, right? We want to convert them before we solve. So I need to convert kilometers to what? Meters. And I want to convert minutes to seconds. Right? It's going to be easier to do it before you do the velocity part of it. So 40 kilometers would be 40,000 meters. Right? And 32 minutes we're going to multiply by 60 to get to seconds. So velocity equals 40,000 meters over 1920 seconds. And my velocity comes out to be 20.83 meters per second. Agreed? Now it asks for it in kilometers per hour. So there's a couple ways we could go about doing this. Do you remember the shortcut to convert from kilometers per hour to meters per second? Or vice versa? Right? The shortcut is 3.6. Right? If I want to go from kilometers per hour to meters per second, I divide. If I want to go meters per second to kilometers per hour, I multiply. So I'm going to go 20.83 times 3.6. And I get 75 kilometers per hour. Okay, let's say that I forgot the shortcut, right? If I wanted to go kilometers per hour, I would just go velocity equals 40 kilometers divided by, let's say, 32 divided by 60.53 hours. And I get 75 as well. Right? All I did here was convert my 32 minutes to hours, and then I did my kilometers per hour that way. So you could solve the velocity or you could just do the conversion. It doesn't really matter there. So speed has the same technical equation as velocity, except you use distance, not displacement. That's the only difference. It's distance divided by time rather than displacement divided by time. Okay? So here's just a couple things with speed. Distance is not displacement. It cannot have direction because it's only a magnitude, right? Speed can never be negative because negative tells us direction. So speed is just an average of your total distance divided by total time. Right? That's a really, really important difference there. Total distance divided by total time. Okay? That's why in your car it's called a speedometer, not a velocityometer. Right? Because your speedometer can tell you direction, and it tells you exactly how fast you're going right now. Right? Try this one on your own, and then we will move into our assignment. So this one is really, literally as easy as it seems, right? If I'm going to solve for this, I'm going to take 100 meters divided by 12.2 and get 8.19, 8.2. Is that right? 8.2 meters per second. Okay, that's pretty fast. What's my direction here? Because velocity has to have magnitude and direction. So what's my direction? It doesn't give us a cardinal direction, so I can just keep it as positive. Right? I can just keep it as positive. You don't have to necessarily include the plus sign to tell me positive. If you leave it as positive, that's an indicator that they're moving forward. So you can leave it off if you want to. But you don't add a cardinal direction unless they give you a cardinal direction. So you wouldn't say north because you don't really know, is she running north or is she running east or whatever. Okay?